So now that we've talked about how to construct molecular orbitals, I'd like to talk about bond order. And that's really just the difference between the number of electrons that are in bonding and anti-bonding orbitals. But we interpret it as is the number of bonds that exist between the two atoms that are coming together to form that molecular orbital, or more atoms, right? So our bonding order equation is the bond order is equal to the number of bonding electrons minus the number of anti-bonding electrons divided by 2. Now, we're only going to consider the valence electrons for this. All of our core ones should be paired up. And we have to be comfortable with the fact that this might be a fraction. It might be 1/2, it might be 5/2, it might be 3/2. And we'll see that the higher the bond order, the stronger and shorter the bonds. And so a higher bond order is going to correspond to basically having more shared electron density between those two atoms or within the molecule. And so that bond order, as it increases, it's really bringing the nuclei together. We'll have shorter bonds, we'll have stronger bonds, like 2 bonds instead of 1 bond. Now, if the bond order ends up being 0, then it's unstable and it's not going to form an actual bond. So a bond order of 0 would tell us that no bond forms, and this is not actually a molecule that you're going to find. So let's go back up and look at this for the hydrogen atom we just discussed. So if I want to calculate the bond order for this hydrogen molecule, my bond order, which I'm going to abbreviate BO, is going to equal the number of bonding electrons minus the number of anti-bonding electrons divided by 2. So in this case, I have 2 bonding electrons minus 0 anti-bonding electrons divided by 2, or a bond order of 1. So this would tell me I have equivalent to just 1 bond between them, which makes sense. They're sharing 2 electrons. This matches perfectly with our idea that we had back for Lewis theory, for Vesper theory, for valence bond theory. It's nice and consistent. Let's look at another example. Let's look at helium. This is another simple one. Where we're only working with s orbitals as atomic orbitals. So in this case, when we create the same looking molecular orbital diagram that we did for hydrogen, right? We just have more electrons right here coming from each of our atomic orbitals to contribute to the molecular orbital. And so when we do that, we have 4 to work with. So we'll first occupy our lowest energy level right here, and we'll have our 2 electrons in the bottom. And then after that, we'll occupy the higher anti-bonding orbital, and it'll take 2 electrons. And then I've used all 4. So then my bonding electrons, I have 2 of them, and I have minus my 2 anti-bonding electrons. That gives me 0 divided by 2 gives me a bond order of 0. Therefore, 2 helium atoms don't bond together. A bond doesn't form if my bond order is 0. There's no net bonding. That's another way to say it.